Alright, what's up guys? This is going to be a pretty short video about apparent weight. I was supposed to talk about this in class tonight, but I ran out of time as often happens, so we're just going to do this in a video here. So, okay. This is the situation, right? You're riding in an elevator, and the question we want to answer is, how does your apparent weight change depending on the acceleration of the elevator and the magnitude of that acceleration? So we've got two diagrams here, right? On the left, this is well, it's you. Look at how happy you are. Probably because you're learning about physics. Don't ask me why, you don't have an egg. But anyway, in all seriousness, on the left-hand side here, it's just the free body diagram, right? And for clarity, I kind of move things around a little bit, but on the left-hand side, the acceleration is up. Okay, so you and the elevator are, accelerating at the same rate, and you're accelerating up. On the right-hand side here, same exact situation, except now the whole system is accelerating down. Okay, so let's do this. Let's just sum the forces using, or rather thinking about Newton's second law. So everything's happening in the y direction here. So what we have here is for, let me say for the case where the acceleration is upward. All right. And we're just gonna do the math, and we're going to apply Newton's second law, and we're just gonna kind of see what that suggests. All right. It might be difficult for this to, or for me to make intuitive sense to you, but the math is pretty clear in what it suggests. All right. So for this left-hand figure here, we're gonna say n minus mg. This equals ma. Okay, and everything I'm writing here is positive, right? So all the numbers, whatever these numbers are, will work out to be positive. If we were to, I shouldn't say work out to be positive. They are positive, okay? So I'm putting the appropriate sign in to indicate that, like, this gravitational force, say, points down, and, there's like an implicit plus sign here in front of the normal force to suggest that it points up. And over here, same idea, right? So I'm talking about the magnitude of the acceleration, which means that this whole quantity here on the right is positive. So anyway, it's pretty straightforward, I think. What we do is we just say that the normal force is equal to mg plus ma, right? And we can tidy this up. We just factor out the m, and then we write g plus a. Okay, so this is the situation where the elevator is accelerating upward. So you see what happens is your normal force gets larger. Okay, and that's all well and good. But, what this is kind of supposed to describe maybe is you imagine you're standing on a scale, right? So you've put a bathroom scale down or something on the elevator floor, you're standing on it, and what you would observe as this thing accelerates up is that your apparent weight, right, which is the weight that the scale is reading, increases. And that's because what the scale is reading is the normal force on you, right? So you could also imagine something I discussed in class earlier tonight, where if you're standing on a scale, right, and someone comes up and puts their hands on your shoulders and starts pulling you down, the scale would read a larger weight. Okay, and I mentioned this in lecture, and I said something like maybe there are some springs in the scale that compress depending on how heavy you are, and there are some sensors or something that convert that into a weight or a mass, right? For our purposes, it's kind of the same thing, at the surface of the Earth. And this is sort of the same situation, okay, where it's not like your mass is actually changing, right? But the force that is exerted on you by the scale is increasing, because you're exerting a force on the scale, and it's exerting the same magnitude of force up on you. All right. So anyway, the TLDR is that your normal force in this case is essentially just your normal weight plus this factor of mass times acceleration. Okay, so you could plug some numbers in and see what happens for different accelerations. All right. Let's talk about the case now where, let's say, the case where the acceleration is downward. And I can just copy and paste pretty much this whole line here with one important change. Let me just copy and paste this part. So all we're going to do here is we're going to put a minus sign in front of the MA term, right? Because this is the same thing as saying m times negative a, right? And acceleration's a vector, so we need to specify the direction, and we're going to do this by putting a minus sign in front of the a. But it looks better. It's just nicer to write negative ma. Okay, so then we're going to solve for the normal function again. In this case, it just works out to be m times g minus a. All right, so kind of to summarize what's happening here is when the when the elevator is accelerating up, right, your apparent weight increases. And maybe you've noticed this if you've ridden on an elevator, right? I'm assuming most of you, if not all of you have. Maybe you notice that like when it starts to move, you feel a little bit heavier. Move up, that is. Now, when it moves down, your apparent weight decreases, okay? So it's going to decrease by an amount, ma, where m is your mass and a is the magnitude of the acceleration. And maybe I don't even need to say this, but let's just say for the case where the elevator is not accelerating, or even moving at constant speed. Let me just make sure that this is phrased the right way for the elevator's not accelerating, or even. Well, okay, actually, this is a bit redundant, isn't it? Because what I'm trying to say, okay, so what I'm trying to say here is the elevator could be moving, or it could be stationary, right? And this result that we're about to find is the same, and I don't think there's anything shocking about it. But it's the same in both cases, which is maybe a little bit weird. So let's just write this out very fast. But this is the simplest of them all. It's just n minus mg equals 0, right? Because the elevator could be moving at constant speed, in which case the acceleration is 0. Or it could just be stationary, that is not moving at all, right? And the acceleration is 0. And the second law doesn't really care, right? It doesn't sort of differentiate between the two of those situations. Anyway, you find that in this situation, it's just that your normal force is mg, okay? I think that's pretty much it. We could also talk about one more thing. I don't know if this is on the homework or not, but like it's worth mentioning. But let's just say one more thing is this. Let's say for the case where the elevator is in free fall, and this is a terrifying thought because this means that maybe the cable has broken or something like that, right? And I hope none of you ever experiences this, but it's interesting from a physical perspective. What this means is that the acceleration is now a equals negative g. Okay, so we can do this one more time. You can probably see where this is going. But we sum the forces in the y direction. We have that n minus mg equals negative mg. Okay. I don't know if I like calling it negative g. Let me say this. I'll just say a equals g downward. All right, that will hopefully sidestep any confusion about the sign here. So what I'm saying now is that this is negative ma, but a is just g, right? So it's accelerating downward with the magnitude of g. In this case, what we find is this. We find that the normal force equals mg minus mg. Okay, the normal force is 0, so you wouldn't experience any normal force, right? This is kind of like in the cartoons when like somebody's standing on a I feel like I've seen something like this before, where somebody's standing on an elevator, and you know, the cable breaks or something, and then the elevator falls, and then the cartoon character is just still standing there, like floating in midair for like a couple seconds until, you know, gravity catches up with them or whatever, and they begin to fall too, right? But you know, the normal force is in fact 0, and you know, this is perfectly consistent with your feet like losing contact with the floor of the elevator, right? Because you know, whenever there's contact, there's a force, and so normal force being equal to 0 kind of implies that there's not contact, right? And this is what happens. Your normal force goes to 0. All right, and again, terrifying thought, and I hope nobody ever experiences this, but it is interesting to look at within the framework of Newton's second law. So I think this is all you really need to do that one problem on the assignment, and you know, this is something that is always mentioned in a class like this, so I felt like I should talk about it a little, but this is basically it.